The purpose of this video is to review or learn how to identify significant figures or significant digits in measurements. Basically, I would like you to be able to never make this face that this poor little girl is making when somebody asks you how many Sig Figs should an answer in physics have. There are three initial definitions that you should write down in your notebook. Number one, a significant digit or a significant figure, or what we call Sig Figs, are digits that show the precision of a measurement. And there are rules to identify those significant digits that we're going to talk about later on. There are placeholder digits. Placeholder digits just show the magnitude or size of a measurement. They just show how big or how small a measurement will be. And then the last type of digit is the cosmetic digit, and it's the zero that is placed before a decimal point if the number is less than 1, just to make the measurement easier to read. So why do we need to know about these types of digits? We need to know about significant figures because the number of decimal places in a measurement tells us the precision of that measurement. Rule of thumb, a measurement can only be as precise as the lowest number of significant digits that can be read off a piece of equipment. We're going to talk more about that the next day after this video because we're going to learn how many decimal places to record measurements using different pieces of equipment. So what's the difference between accuracy and precision? Accuracy is defined as how close a measurement is to the accepted literature value. For example, we accept that gravity has an acceleration on the planet Earth of 9.81 meters per second squared. So we say a measurement is accurate if we get close to 9.81 meters per second squared if we calculate our measurements correctly. However, precision has to do with how close a group of measurements are to each other. So how many trials you perform during an investigation and after each performance of the procedure, how close those measurements are to each other. That's what we define as precision. Let's look at a visual example of this. So here are 4 targets, and the center of the target, where the crosshairs are located, is where whoever was shooting these darts was aiming. And let's take a moment here to see which one of these dartboards represents an accurate shot, a precise shot, or none of the above. So if you look at target A here, target A, all of the darts almost hit the bullseye, and they were all grouped together. Therefore, what we can go ahead and say is that this particular target, and shooting towards that particular target, shows a level of accuracy and precision. That's because all of these darts were really close together and almost hitting the crosshairs. In target B here, target B in the center, all of the darts were clustered close together. However, they all missed the target. So we can say this particular person has a high level of precision because all of the darts are really close together. However, it's not accurate. And again, not accurate because he was, or she was, pretty far away from the target. In C and in D here, we can say that neither one of these shows accuracy because all of the darts are all over the place, and they're not precise either because all of these darts are all scattered away from each other. So neither one of the targets C or D shows accuracy or precision. We could argue that target D shows a little more precision because the majority of the darts were in this fourth quadrant here, but I would also argue that it's pretty much showing no accuracy and not a lot of precision. So that's a visual representation of accuracy and precision using a target practice model. Let's take a look at a real scientific model. So let's pretend here that this particular scientist was trying to measure the literature value for the acceleration of gravity on the planet Earth, and they performed 3 trials, and these were the 3 trials and 3 measurements that the scientist obtained. The literature value, the accepted value for acceleration, gravitational acceleration on the planet Earth, is 9.81 meters per second squared. Take a moment and pause the video and make a decision whether or not these values are accurate, precise, or both. Hopefully at this point you realize that these values showed both accuracy and precision. And again, because these values are really close to the 9.81, and a little bit later on we'll learn how close you need to be in order to consider measurements accurate. Also, you'll see here that all of these measurements are grouped pretty close together with a range of no more than 0.15, which means that shows a pretty high level of precision. So I would say that these particular measurements are both accurate and precise. So now let's take a look at how many decimal places we should record measurements to. And that means we have to learn rules about significant figures, placeholders, and cosmetic digits. There are 6 rules to remember. I would take a moment to pause the video and write all 6 of these rules down. On the next slide, you will see a visual example showing leading zeros, trailing zeros, sandwich zeros, and we'll be able to identify these different types of digits in an actual measurement. So again, please pause the video and write these down, please. So here's the visual example that I promised you. So this measurement is some length in centimeters. The first zero here is that cosmetic zero we were talking about. That cosmetic zero is placed before the decimal point if the number is less than 1, just to make the number look a little bit more balanced. It's something that we learned how to do when we were writing decimals in elementary school. So that's called a cosmetic zero. The next type of zeros here are placeholder zeros. And all those placeholder zeros do is tell the size or magnitude of the measurement. In this particular case, the measurement goes to the thousandth of a centimeter. So these zeros just show the size of the number. They are not significant. All of these values here, the 4, 4, 5, those are significant because they're not zeros. They're the easiest ones to identify. These zeros are what we call sandwich zeros. And they're sandwich zeros because they're sandwiched between the 4s on either side. Any zeros sandwiched between 2 significant digits are also significant. And then last but not least, and these are the hardest for students to recognize, are the trailing zeros. Trailing zeros to the right of a decimal are significant because they show the precision of a piece of equipment. Whatever caliper we were using to measure whatever this person was measuring can measure out to the 1, 2, 3, 4, 5, 6, 7, 8, 9th decimal place. That means that I have to record 9 places behind the decimal. So these trailing zeros here are significant. So take a moment here, and I would write down this visual representation because it's a good one to show the different types of digits in a measurement. The only one that's not represented here is the counting numbers. And when I count something, I am certain about those numbers. For example, I am certain there are 12 eggs in a dozen. Therefore, the 12 has no significant digits or both significant digits because I am completely certain there are 12 eggs in a dozen. Let's do some practice. Take a moment and see if you can identify how many significant figures, Sig Figs, significant digits are each one of these measurements. And then unpause the video and see if your work compares with mine. Hopefully you'll see in the first one here, I have a 1 and a 5 at the end, both significant. That makes all of these zeros sandwich zeros. Therefore, in number 1, there are 6 Sig Figs. In the second one, this 0 is not significant because it's a cosmetic 0. These 2 zeros just show the size of the volume that was measured, and it shows that the volume here goes out to the 1000th spot. So these are not significant. They are placeholders. And so in this one, there's only 1, 2, 3 significant digits, or Sig Figs. The last one, the trick question. I bet you put down 3 Sig Figs. That's not the correct answer in this case. That is the acceleration due to gravity on the planet Earth. That is a literature value or an accepted value. That means in this case, we are certain about all 3 digits, and that means that the accepted value either has no significant figures or all 3 are Sig Figs. Literature values, we usually do not count those when we're counting significant figures. That's because we know all those digits are significant. Now let's figure out how to perform mathematical operations with these particular significant figured measurements. 2 rules. Please pause the video and write these down. First rule, addition and subtraction. Addition and subtraction, when you are adding or subtracting measurements, you will round to the smallest number of decimal places, smallest number to the right of the decimal. However, when you are multiplying and dividing, you will round to the smallest total number of significant figures in the measurement. And we will give you examples of those on the next slide. What I have done here is I have gone through and done calculations based upon the operations I see, and I have not yet rounded to the correct number of significant figures. So in the first one here, I'm adding, and if I look at each one of the measurements, I'm going to count the number of decimal places to the right. 3.4 only has 1 decimal place. Therefore, I'm going to round this measurement to the 10th spot, or the first place behind the decimal. I look after the 8. It's a 7. 7 is greater than 5. So that moves 8 up to a 9 to make this 10.9 centimeters. So again, when adding, I round to the lowest number of decimal places. Second example, I'm multiplying. And when I multiplied these values out, it's interesting to note here that the seconds cancel out, leaving with a length in meters. This is a way to find distance or displacement if I know a velocity or time. So now that I know I'm multiplying, I'm going to round to the lowest total number of sig figs. Each one of these has 4 significant digits. So I'm going to count 1, 2, 3, 4. I look after the 8. It's a 2. The 2 is less than 5. So that means the 8 stays the same. I turn this into 13,580 meters. And then the last one I haven't quite completed yet, because if you notice here, I have 2 operations. And when I'm rounding to the correct number of sig figs, I have to follow PEMDAS, or order of operations. Please excuse my dear Aunt Sally. First step is what I'm showing you here, and I added 45.2 plus 1.432, and I got 46.632. I have to stop here and round to the smallest number of decimal places, or 46.6, because the 45.2 has 1 decimal place. The last thing I'm going to do here is I'm going to multiply these values together, and I get 415.02. But I notice here I've got 1, 2 significant figures. So I have to start at the very first digit and go 1, 2. I look after the 1. It's a 5. That rounds the 1 up to a 2. So notice how incorrect my measurement appears to become. It turns into 420, and I don't know what the units are on this one. So it's really important to know every single time I round a measurement after I perform a step, my answer gets more and more imprecise. That's why I taught you isolating the variable first, because if you isolate the variable first, you can usually perform all your steps in one step, and you don't have to round your answer until the very end. Saves you a lot of time and a lot of energy. So at this point, make sure you go back through the video, make sure you understand accuracy, precision, make sure you can identify significant figures, cosmetic figures or digits, and placeholders. Make sure that you can add, subtract, multiply, and divide with measurements with correct sig figs. And then you're going to do some practice by doing page 20, numbers 1 through 4 from your physics text, page 28, 15 through 22. And we are going to go over these problems on Wednesday. Thank you and have a wonderful evening.